Good morning, everyone.
Good morning, sir.
So I was having a look at your syllabus and the pace at which we are going. So I thought that we have already covered this 8086 microprocessors fundamentals, right? Now the portion that is left is interfacing devices, which is a very important topic. And the second topic is 8051 microcontroller. These two topics are left from your syllabus, and we have sufficient time to cover these topics in detail. I mean, up to the extent in which the syllabus requires us to do. So the thing is, my initial plan was to give focus to 8086, which we have already done. The second thing is I want to give focus to this interfacing devices, right? Because ultimately, you as an engineer should be able to assemble your own computer system if a microprocessor is given to you, right? So we will be dedicating most of the time to that interfacing thing. And the last topic, which is 8085, 8051 microcontroller. As you already know, that microcontroller happens to be a system on chip. I mean, there will be the microprocessor as well as its peripherals, which are interfaced with. I mean, the peripherals will be there on the same electronic chip, on the same single chip, right? So this interfacing, etc., you don't have to take care of that. So there is nothing much to learn in that. I mean, there is this brain part of the system, peripherals are also attached. So all you need to learn is programming. And I do not now want to overburden you with a new set of programming instructions for 8051. So what I have planned for 8051 is, for 8051 we will be just seeing its architecture and pin diagram and what all peripherals are already attached to it on the chip itself and how they operate. So that portion is what we will be focusing on, and I don't want to dedicate more than 4 or 5 lectures for that. So that we will take at the end of the course. So we will cover 8051 from the theoretical perspective, because that way, there are many microprocessors in the world. We could also include Pentium 1, 2, 3, 4, then Core i3, Core i5, Core i7. They have their separate instruction set, separate architecture, etc. So we can't learn everything. The purpose of this course was to be able to grasp one microprocessor completely and learn some interfacing. So that's what we will focus on, right? And as I was seeing the course completion that we have done by now, so for 8086, since we have completed the fundamental part, only interfacing part is remaining. So interfacing part, I will postpone it till the time we have some more grasp on 8086. So the next week or next 2 weeks, we will be dedicating for the programming of 8086. We will make various programs. So that way it will be easy for us. I mean, it will be easy for all of you to have a complete grasp of the entire instruction set of 8086, which has 100 instructions, and many combinations out of those instructions can be made, right? Because as a part of instruction set, we have only covered up to arithmetic instructions, right? There are many more instructions. Apart from instructions, there are some good practices of programming which we should also learn for 8086. So the next 2 weeks, since we have much time left, so the next 2 weeks we will be dedicating for programming. So I'll be telling you some good things like data structures, some kind of apart from that, some good programs like how to deal with multimedia on this 8086 system. So will that be okay with all of you? Or should we proceed with, I mean, there is an alternative option that we should read the interfacing as quickly as possible, and then we should read 8051 in depth, which is not required as per our course, but that will be another burden of programming language. So there is a different set of instructions, how to deal with them. So that is an alternative option. So what do you all say? What should we do?
Programming, sir.
We should do 8086 programming, yeah, because that will make us more future ready once you master one microprocessor completely together with the interfacing. So if you go to the industry, then there will be their own microprocessors, and they have their own interfacing devices, and they would like you to exercise some control over those devices. So that way you will have this training here itself. So for the next 2 weeks we will try to learn some good programs of 8086 with some best practices, right? Also I will introduce these interfacing devices slowly one by one, right? So we will introduce one device per week, and the programs related with that we will make together with that in that lecture itself, right? So that's what we are going to do for the next 2 weeks. After which we will have our mid-semester examinations, and after mid-semester examinations we will start 8051 microcontroller, right? And that too we will cover from theoretical perspective. So that is the plan for the coming lectures. And yesterday, since I told you that in examinations there could be questions like you will be given 8086 microprocessor, and I will tell you to interface memory or interface some peripheral input-output device and make the circuit for that, and then you have to write a program to be able to transfer some data. So since I have told this to you, there were few requests yesterday that they again want to understand how memory is interfaced, right? So today I will again tell you the example that we were doing on the last term, because that was half term. So we will be continuing with that example, as well as we will also see how to interface that dynamic RAM, because static RAM is we have already dealt with. We will understand what dynamic RAM is and how it is interfaced and why it is useful and what are the drawbacks of dynamic RAM and what are the advantages of dynamic RAM. So that is the content of this today's lecture that we are going to cover. So let me begin by just taking the second example that we were dealing with on the last term. So this was the example that we had on the last term. Can somebody quickly explain me what is going on here? Let me open it with another browser. Yeah. So can somebody explain to me this in 5 minutes so that I can proceed from there onwards? Remember, there has been a notice that some of you are not attending the classes for the full length of time. So you just make a login and you log off. So that way, remember, you won't be given any attendances, and management is very strict about this. So people might not be able to give their mid-semester examinations if the attendance is not sufficient. So attendance is sufficient, participation in class is encouraged. That is how you will be able to learn. So that is something that I want to brought to your notice. Now, can somebody tell me what is written on the screen and what are we doing for static RAM interfacing here? And remember, there will always be marks for participation. Now, someone please explain to me what is the problem that we are trying to solve on the screen.
Sir, according to problem, there are two EEPROM cross 8 and two 32K cross 8 RAM. So we are trying to attach them and the RAM address must start at 00000H. So we are trying to attach them, and for ROM, we are compulsory that it should contain FF0H. So we are trying to attach them.
Okay, so why do we have two set of RAMs and two set of ROMs here? Why not one RAM and three ROMs?
To implement the even and odd bank.
Even and odd banks. Okay, okay. So since you all people requested that you want to understand this problem again, so let me again illustrate this static RAM interfacing. Then we will move on to the dynamic RAM interfacing. Right. So the problem that we are addressing here is we have a 8086 microprocessor system, and that microprocessor system can at max have 1 megabyte of externally interfaced memory, right? But it is usually not the case. It is usually not the case that we interface complete 1 megabyte of the memory, right? So, for example, you might have seen in your mobile phones also that suppose for a particular phone model you have got 16 GB, 32 GB variant, and the memory is expandable up to 128 gigabytes, right? So same happens with this microprocessor also. You do not interface the full 1 megabyte memory. You interface only few part of the memory which is useful to you, and then after the remaining portions are left. Either some input output devices are attached to it, or they are just left as it is. Why? Because memory is a costly thing, and if you try to use the full memory, it is of no use. So that is why in this problem, if you see, they are saying that design an interface, because whatever we are now going to attach is not a part of 8086 integrated circuit. It has to be interfaced to 8086 by making proper electronic connections, right? So they are saying design an interface between 8086 CPU and two chips of 16K cross 8 EPROM, right? So you have got two ROM chips. Their size is 16K cross 8. Cross 8 means every location will be of 8 bits or 1 byte, and 16K means there will be 16K locations, right? 16K locations. So K means 2 raised to the power of 10 and 16 means 2 raised to the power of 4. So there will be 2 raised to the power of 14 total locations, and each location is capable of storing 8 bits or 1 byte, right? So you have two ROM chips of such kind. I mean, two 16K cross 8 ROM chips are there. So you will be having total 32K cross 8 addresses. Sorry, 32K addresses. 32K means 32 is 2 raised to the power of 5 and K is 2 raised to the power of 10. So you have got a total of 2 raised to the power of 15 address lines. 2 raised to the power of 15 address lines. 15 address lines, or 2 raised to the power of 15 total addresses, right? So that way, address lines from A0 to A14 will be used, because they will mean that you are using total 15 address lines for this EPROM chips, and not single EPROM chip, a set of two EPROM chips, right? Similarly, you have got 32K cross 8 RAM chips, and they are also 2 in number. So ultimately you have 64K cross 8 RAM locations, and 64 will mean 2 raised to the power of 6, and K is already 2 raised to the power of 10. So you have 2 raised to the power of 16 such memory locations for 2 chips, and 16 address lines will be used. So from A0 to A15, if you talk about the RAM addresses, then A0 to A15 will be used, and every location in RAM is also of 1 byte in size, right? So that is our problem. They have given us 2 ROM chips and 2 RAM chips, and we want to interface that to the 8086 microprocessor, and they have given us one constraint: select the starting address of EPROM, that is ROM, suitably, right? So ROM addresses are to be selected suitably. What do we mean by this? We have already said that when a computer resets, the execution begins from FFFF0, the actual physical address, 4 times F and then 0. So from that address, the operating system of this 8086 microprocessor is written. So that address should be used when the computer is reset. And where are the programs written when the computer is reset? Because operating system is a relatively permanent thing. You do not change it frequently. So will you be writing it in ROM or will you be writing it in RAM? Will you be writing your operating system in RAM or will you be writing it in ROM? Because operating system is a permanent entity. So where will you write it? In RAM or ROM? Any answers?
ROM.
In ROM. Obviously, you have to write that in read-only memory. So that is why they have written this line: select the starting address of EPROM suitably. So EPROM must include the address FFFF0, right? FFFF0 should be included by EPROM. And then they have given us a second constraint that the RAM addresses must start at 0000H. So RAM should start from the starting of the addressable locations, right? 0000H. So these are the two constraints given to us together with 4 memories, I mean 2 ROMs and 2 RAMs, and we are supposed to interface them with the 8086 microprocessor. And for that, we have to make some hardware connections. In this example, the highlight is that you have got ROM and RAM of different sizes. ROM is 16K cross 8 and RAM happens to be 32K cross 8. That is why different number of address lines will be used for both. And the second thing is there will be some gap. Between two chips of RAM and two chips of ROM. Two chips of RAM will be combined at continuous memory locations, and two chips of ROM, they will also be combined at continuous memory locations, but there will be some gap between the two. So why does that gap comes into picture? We will just notice it. Now, so let's fix this ROM first, right? We try to interface that these two ROM chips first. 16K cross 8 ROM chips are there. So let us try to interface them first, right? So 16 cross K8 two chips are there. It is why 32K cross 8 locations are possible. And on that note, we have 15 address lines. Since 32K will mean 2 raised to the power of 15. So 15 address lines, that is lines from A0 to A14 have to be used for the two EPROM chips. For two EPROM chips, we will be using addresses from A0 to A14, right? So since these addresses are to be used, and we need to include FFFF0 into the ROM address space. That is why we need to connect these ROM chips at the end of the addressable space. Because if you see the end of the addressable space, it is FFFF. So FFFF0 will be near to this number instead of taking it from 0000H. So FFFFH, since it is near to this number, we will start interfacing our ROM chips from here. So let us calculate the address from where the ROM chips will begin. So we already know that 15 bits, that is A0 to A14, will be consumed in that. So for EPROMs, for a set of two EPROMs, I have written 15 ones here, right? From A0 to A14, you can notice I have written all ones and rest all values are 0. So that way, if you group them in a pair of 4, you will get the number as 07FFF. 07FFF is the total size that this two EPROMs will be consuming in hexadecimal, right? 2 raised to the power of 15 in hexadecimal is 07FFF. So this is the size that these two set of EPROMs will consume combinedly. So since I am trying to interface these two EPROMs from the end of the addressable space, so I will subtract this number 07FFF from this FFFF number to get my beginning address. So these three F's of the end will make these three F's 0, and you have got a 7 here. So F minus 7 would be 8, and then you have got a F here and a 0 here. So this will be F. So F8000 in hexadecimal will be the beginning address of the set of these two ROMs. And these set of two ROMs will be connected between addresses F8000 and FFFF. Right? Now, does this address range include FFFF0? Does this address range include FFFF0 address? Yes or no? It includes that. So that, yeah, is somebody asking something? No. So
No, sir, I will. Yes.
Okay, that is okay. So that is why you see this second constraint is met. The first constraint is met. Select the starting address of EPROM suitably. So we are selecting the addresses of EPROM such that whenever the computer is reset, the program which is written in ROM will be executed. So that is the case. That constraint has been met here, right? Now, the second thing that we are doing here is we want to fix these two ROMs, 32K cross 8. So since they are 2 in number, so 64K will be there, and 64 will mean 2 raised to the power of 6, and K will mean 2 raised to the power of 10. That is why you will have a total of 16 memory locations. 16 memory location, and that means you will start from A0 and go up to A15 for deciding the addresses of two set of RAMs that you are going to use. They have already given us this constraint that the RAM address must start from 0000H. So since the starting address is fixed, let us fix the starting address 0000H. So in binary, it will be all zeros, right? Now, what will be the last address of this? How will you calculate the last address? Convert 64K into hexadecimal and subtract and add it to this 0000H. Yes or no? Convert this 64K for the two chips into hexadecimal number and add that hexadecimal number to the beginning location, so that you will get the last address, which is 0FFFFH. So that's what we are going to do. So here you can see in the second line for two SRAMs, I have written the addresses such that from A0 to A15, that is a total of 16 bits have been 1 and rest all are 0. So if you convert it to a hexadecimal number by grouping it into 4 numbers as you have seen here, you will get 0FFF, right? If you add this 0FFF to the initial address 0000 for the actual physical RAM, you will be getting the last address. So the last address happens here to be 0FFFFH. So this address range is fixed for your two set of RAMs, and the constraint that it must include the address 0000 as the beginning address is already satisfied. So are the addresses clear to everyone?
Yes, sir.
So I think the addresses are clear to everyone, and now after having these addresses known, now our purpose is to connect these ROM chips and RAM chips. We have got these two ROM chips and we have got these two RAM chips. We should connect them to the computer system. We should connect them to the 8086 computer system. Now, just knowing the addresses is not enough, right? Because in 8086 we know that we have the memory chips which are organized as odd and even memory banks on the account that we want to write a one word data in one machine cycle. That means 16-bit data should be written in one machine cycle. If you see here, every location in memory is of 8 bits or 1 byte, whether it is ROM or RAM. But 8086 is a 16-bit computer, and if you want to write the complete 16 bits at one machine cycle, or 2 bytes in one machine cycle, or in alternate words, one word in one machine cycle, then what you have to do is you have to organize your externally interfaced memory into two banks. One is odd bank and another is even bank. So we have discussed the logic for this. I mean, by using this BHE bar and A0 signals, you will be able to divide your memory chip into two parts of odd and even bank. And we know that if you want to access the even memory addresses, you have to activate A0. And otherwise, if you want to activate odd memory bank, you have to activate BHE bar signal. If you want to access both of them in one machine cycle, then you have to activate BHE bar as well as A0 at the same time, right? So that's what we have to do. And keeping that in mind, we have to design our system. So let us talk about these two ROM chips first, right? Two ROM chips are connected here. Now, here if you see, okay, let me just show you the relevant slide for even and odd memory organization so that things will become further clear to us. So, okay, not here. I must have kept them somewhere else. So this is your memory organization in even and odd banks. Right. So this is a pilot example just to give you a quick review of how memory banks are organized as even and odd addresses. So assuming that we have got address lines only from A0 to A3 in one microprocessor, you could either purchase this single memory chip which will have 16 memory locations. Every location will be of 8 bit or 1 byte each, and you can interface it to the microprocessor. But if that microprocessor is a 16-bit microprocessor, that means the data bus of the microprocessor is 16-bit. So at one time the data bus can contain 16 bits of information, and if you intend to write that 16-bit information in one machine cycle. With this structure of memory, it is not possible. It is impossible to do that with this structure of memory, because memory is such that you have to supply address here, and accordingly that whatever address has been supplied, suppose 1000 has been written here, so that location will be activated and these 8 bits can be written into the memory. But if you want to write 16-bit data, you have to write 2 consecutive memory locations, and there is no way by which you can write 2 consecutive locations here in single machine cycle, because 2 different addresses have to be provided here, and those 2 different addresses can be provided in 2 different machine cycles only. So to overcome this problem, we have come up with an idea of odd banks and even banks. So instead of buying this memory chip which has got 16 locations, we will take a memory chip which has got 8 locations and 8 locations. We will take 2 sets of that, and if you see, only A1, A2 and A3 bits of that. So for the even locations which are marked in yellow here, and for the odd locations, for one combination they will be same. So if you see in this 0 and 1 combination, first 3 bits are same, 0, 0, 0, 0, 0, 0. Similarly, if you see in this second combination, 0, 1, 0 and 0, 0, 0, 0, 1, 1, this first 3 bits 0, 0, 1 and 0, 0, 1 are same, only 0 and 1, this is different, 0 for even and 1 for odd. So on that account, instead of taking these 4 address lines as input, in this odd memory bank or even memory bank, there will be only 3 address lines as inputs, because there are 8 possible locations. So we will attach A1, A2 and A3 to that, right? So that way you will be selecting the 0, 0, 0, 0, 0, 1, so on and so forth, and the same lines will be there also, right? But if A0 is equal to 0, then that's an even memory bank, and if A0 is equal to 1, that would be odd memory bank, right? So this A0 signal, it is used as an activator of this even memory bank, and for the odd memory bank, the activator that you are using is bus high enable bar signal, right? So BHE bar signal is there. So if this signal is 0, then this signal is activated, and since this is active low chip, because the bubble has been attached after that, so this will be activated when your this BHE bar signal is 0. That means BHE is activated, right? So that's what we are going to do here. And now in one machine cycle, you can provide addresses to both of these chips, A1, A2, A3. These are they come from the same address lines, and they can be attached here by taking 2 wire connections from them, and they can be attached here, and A0 can be connected here, and BHE bar signal can be externally attached to this. So in one machine cycle, you will be able to provide the complete address, that is A0, A1, A2, A3, A4. And in one machine cycle, if one intends these both locations, for example 000 and 0000 of this, that is actual location 0 and 1, that is these 2 locations can be simultaneously activated, right? So this is the pilot picture of the entire thing. In our question that we are trying to solve, we are using the same thing here. You have got 2 16 cross K EPROM chips. So we already said that since 32K addresses will be available, so that would be 2 raised to the power of 15 addresses, and that way you will be using A0 to A14 address lines. So in the similar way as we did in the pilot example, we will not be connecting all the address lines to one chip, because one chip is half the size of the entire memory that is we are going to address. So instead of connecting A0 to A14, we will leave A0 and we will connect addresses from A1 to A14. So that is why you can see here these A1 to A14 are connected to both of the ROM chips. Both of the ROM chips have these addresses A1 to A14, and they are connected to them. Now, why is A0 left? A0 will be used as an activator for even bank, and for ROM chip it will be used as BHE bar will be used as an activator. But we cannot apply directly this A0 here as the CS2 activator and BHE bar as the activator of the odd chip. Why? Because apart from doing just activation of odd and even bank, we have to do some other functions also. So let me just show you a chart for that. So if you again see this table, here I have written this A0, BHE bar, and these bits are there. I mean, 13 bit is there. So this is for the previous example. For our case, it will change to, this is A0 and the rest of the bits will change here. So this A0, A1 and A2 has no meaning for us. This was for this decoder. And here we are only talking about, first of all, A0 and bus high enable. So we are talking about A0 and bus high enable first, and this A13 bit in our case will not be used. So some different kind of thing will be used here, which will be used for generating the connection logic, right? So let me just show you that diagram again. So look for this situation, CS2 bar. So for CS2 bar, you see some signal here. This CS2 bar signal, it has been generated from this kind of chip, right? So you have got this NAND gate. The inverted inputs are applied to it. This in turn has been generated from this C signal. So C and C complement signals that you see here, they are not complements of each other. They are actually two different signals, which are not related by C plus C complement equal to 1. They are just two different set of signals. They have been mistakenly written as C and C complement. They do not mean the logical complement of each other, right? So here,
Sir,
yeah.
it did not C dash.
What are you saying?
Sir, is it not C dash?
Yeah, it is C dash, but C dash is treated as, in binary logic, it is treated as C complement. Na? Whether you write a bar over C or you put a complement over here, it is just treated as the complementary signal for C. But that is not the case here. That's what I am pointing out. Right?
Yes, sir.
Okay, so that's what we are doing here. And now let's talk about this C signal first. What is this C signal? Right. So we are talking about, let us say, this ROM chip first. We are talking about the ROM chip first. ROM chip has used addresses from A0 to A14. Now let's have a look at the remaining bits. Let's have a look at the remaining bit for the two EPROM set. So after A14, you can see all the bits are 1. From A15 to A19, all the bits are 1 for both of the sets of ROMs. Right? From the starting address to the ending address, all of the bits will remain as 1. So this is one point. I mean, we have discussed this on the last term, that if you are trying to design a system, then the address lines which will be used by memory chips will be there. Apart from those address lines, the remaining address lines will be used as chip select signals. They will be used as chip select signals. So that is why, we are NANDing all these signals from A15 to A19. From A15 to A19, if you AND all these signals, through a NAND gate, so in case when all of the inputs are 0, this NAND gate's output will be activated and you will receive this C signal. So this C signal could be used as an activator at this CS2 here. But that is not the full story. When will this even ROM should get activated? It will be activated when A0 signal that we have got. Is 0. So A0 signal should be equal to 0. In that case only, this thing should be activated, right? So this signal will be equal to 1. So we will be supplying the complementary input. I mean, there is a bubble here. That is why we will apply a complementary input of CS here, and this bubble indicates that, together with this A0 signal. So when A0 is 0 and when the input at this signal happens to be 1, after this bubble it will be made as 0 only. So when this signal is activated, I mean, all of these are ones, and this A0 is 0. So that means you will be getting the value of A0 as 0 already, and this value will be here. So this CS2 bar chip will be activated. CS2 bar signal will be activated. So this CS2 bar can be applied as a chip select signal to this 16K cross 8 ROM, which is even bank, right? Similarly, for the odd bank, we have got this CS1 bar signal. So let's look at this CS1 bar signal. It is again being made from this BHE bar signal and C signal. So C signal is the activation of all of these inputs. When all of these inputs are activated from A15 to this A19, we know that we are going to deal with the EPROM, so we get this signal. And for activating the odd bank, we have to have this BHE bar signal activated. So that is why this CS1 bar chip has been there, and this CS1 bar can be connected here. So accordingly, the odd and even memory banks will be functioning well, right? So if you look at the other side, I mean for the RAM chips, instead of taking 15 address lines, we will be taking 16 address lines, because 64 means 2 raised to the power of 6, and 2 raised to the power of 10 happens to be your K. So that is why you will be using 16 address lines. So here the address lines will be used from A0 to A15. From A0 to A15, sorry, A0 to A0 to A15, the address lines will be used, and those address lines will be used, and the remaining lines, which are from A16 to A19, from A16 to A19. If you notice that for the two set of SRAMs, from the starting address to the ending address, they are all 0. From the starting address to the ending address, they are all 0. So if these signals remain 0 always, so we can design this another signal, which is C complement, which is not a complement of this original signal. We can call it as C dash, as somebody pointed out. So this is a signal C dash, which is activated when all of these A16 to A19, they happen to be 0. So if they are 0, inverted input, that means 1 will be supplied here, and the NAND gates output will become 0 at that time, so it will be activated. So the C complement signal will be activated for the select lines. But that is not the full story. This cannot be directly supplied to these two set of banks. We need to have the A0 signal again and BHE bar signal again to generate the chip select 4 and chip select 3 signals here, right? So let us see this chip select signal 4 first, because that is for the even bank. So you take one input from here and one input will be A0. So your CS4 signal bar will be generated, and that will be used for this RAM chip. And for the odd bank of this RAM chip, you will be using this CS3 signal, where you can see that BHE bar, which is for the higher order bank activation, and this C complement signal is there, right? So is this process of hardware design clear to everyone now? Is this process clear to everyone?
Yes, sir.
Right. And another important point to notice here is that to the even memory bank only, the lower order byte of the data bus is connected, and higher order byte of the data bus is connected to the higher order addresses. So do you now get an idea of why little endian kind of data storage is being used here? Lower order addresses, that means if you see a combination of the memory, let me just show you this diagram again. If you see this diagram, any combination of even and odd bits, let us start from 0000 and 0001. The even address is the smaller address, and the corresponding odd address will be the higher order address, right? So you have got an even bank, and then you have got an odd bank. So in any combination of even and odd bits, you have to start from the even address only, and even address, because of that reason, will be the lower address, and the odd address will be the higher order address, right? So if you now try to correlate this with this particular diagram, the lower order byte of the data bus is connected to the lower order address, and higher order byte of the data bus is connected to the odd memory bank, which is the higher order address. So from here, the little endian fashion of transferring the data between registers and memory comes into play. Now, is that concept also understood?
Yes, sir.
Is that, yeah. I mean, this is by construction only. When we read the programmer's model, we said that 8086 will function in the little endian fashion. Somebody asks why. So this is the reason, right? Because it has got separation of odd and even memory banks, and that is why, the higher order data bus will be connected to the odd bank, and the even bank will have lower order data bus byte. So that is why the data will be transferred in that particular fashion. Same thing happened in 8085 also, but that was because of different reason. The little endian fashion was followed there, and things happened there in 2 machine cycles if you want to transfer, data from your registers of microprocessors to the stack, because the stack always operates in this 16-bit fashion or 2-byte fashion. So there it was not there by construction, but here it is by construction. So this fact should also be noticed, right? So this is regarding the interfacing of a static RAM and ROM chips. ROM chips, they are not static or dynamic. This terminology of static and dynamic is only used for your RAM chips, right? Which is random access memory. So random access memory is usually used for doing some task, and whenever the task is done, you will free that random memory, right? So it has to be very fast. So now let us see some types of the random access memory in another file. Yeah, so there are two kinds of RAMs, dynamic RAM and static RAM. So there are dynamic RAMs and static RAMs. And static RAMs are very costly. They are used to make cache memories. Static RAMs, they are usually used to make cache memories, which are very fast, And their fastness is just after the CPU registers speed. CPU registers are the fastest to transfer the data. Then there comes the cache memory. So the cache memory is very, very costly. It consumes a significant portion of the cost of your computer, right? So cache memory is very fast, and static RAM is usually a cache memory. So we do not want our RAM to be that costly. We just want we just want a fairly good priced RAM which will be able to do the same task, right? So we come to dynamic RAM. So first of all, let us read this point 6.5. It is very important. So a typical SRAM cell, a typical static RAM cell requires 6 transistors, while dynamic RAM requires 1 transistor and 1 capacitor. So let us discuss this statement, since you are people from information technology and computer science branch. So you need to understand this. For people from electronics and communication, this is very trivial to understand that SRAM will be costly and why does it require 6 transistors and so on. So you might have read this thing in your basic electronics course, that how this D flip-flops are constructed. I mean, in your digital logic course, you must have seen D flip-flops. Yes or no? Have you read these D flip-flops or not?
Yes, sir.
So if you see the construction of those D flip-flops, how do you actually make these D flip-flops? By using certain logic gates. Yes or no? You must have read NOR latch, NAND latch, etc. Have you read the NOR latch and NAND latch, etc.? Yes or no?
No, sir.
Come on, you had a course on digital logic design, and in the syllabus there is this NOR latch and NAND latch. Have you read it or not?
Sir, actually, sir, we were running out of time, so syllabus was not completed.
Syllabus, okay, syllabus was not completed. Okay, so let me tell you, every component in electronics and communication, like for example, if you talk about this entire universe, if you see trees, if you see human beings, what are they made up of? They are made up of cells, isn't it? They are just an assembly of cells. Is it or is it not?
Yes, sir.
Now, cell, if you see again at further levels of resolution, cell is made up of various chemical components. It is made up of various chemical components, right? And those chemicals at their base, they are atoms, right? So everything in this universe that you see is an assembly of atoms. You can say that everything is an assembly of cells, or at another level of resolution, you can say that everything is an assembly of atoms. Or if you go further down, you will say that everything is an assembly of electrons and protons. If you further go down to another resolution, you can see that everything is made up of quark particles. And beyond quarks, let us say we don't know anything. So quark is the fundamental level of design of everything. So in electronics engineering also, a system can be designed at various levels. So you can go to the market and purchase these ICs of basic logic gates and or and not. And you can make any logic circuit. Does everyone agree with this or not?
Yes, sir.
Similarly, for an electronics engineer, even if these logic gate ICs are not available, what they will do is they will buy some transistors. There are transistors, not the radio transistors that you used to listen to in your childhood by tuning them to certain frequency. Transistor is also an electronic component which is very very small in size, of the orders of microns or in these days nano or lower. So those transistors are there. So at one level of abstraction, we say that everything in electronics and communication is made up of transistors, right? So to be able to manufacture a static RAM, it requires six transistors. While dynamic RAM, you need only one transistor and one capacitor, right? So which is a better choice, six transistors or one transistor and one capacitor?
Second one.
Second one seems to be a better choice, but then there are certain problems. If you make a circuit using only transistors, if you make a circuit using only transistors, the transfer of the data between those six transistors will not change the data itself. Will not change the data itself. While if we use one transistor and one capacitor, it will be able to accomplish the work of six transistors, but the transfer of data between transistor and capacitor will lose the actual data originally. And let us understand this in context. Suppose you have got one glass of water, right? And I tell you that you have to preserve this water for 15 years. Will you be able to do it if the glass is not closed, completely airtight, packed?
No, sir.
I tell you to have a glass of water, keep it in sunshine during the daytime, and I ask you that I will ask you for this glass of water for after 15 years. Will there be any water in the glass? No, there will be no water in the glass because of sunshine there will be evaporation. So similarly, in electronic components, right? In electronic components, the logic levels 1 and 0 are represented by some voltages. Let us say plus 5 volt represents logic value of 1 and minus 5 volt represents logic value of 0. So in that case, how is that voltage actually physically manifested? It is manifested as some device has got some capability to hold charge. If that charge is sufficient enough to create a voltage of 5 volts around itself, then we say that that device has got a voltage level of 1 volt logically. And if that charge is negative in nature and opposite in magnitude, minus 5 volt voltage it will be able to generate around itself, then we will say that that electronic component has got a logic value of 0. So that way, these electronic components can be thought of as charge holding devices. And if the surroundings are not perfectly insulated, this charge starts to discharge after some time. And capacitor is a known criminal in that case. With time, capacitor's charge will decay. With time, capacitor's charge will decay. So even if you have stored a logic value of 1 onto the capacitor, after some time you will notice that that has been degraded to 0 value. There is no charge on the capacitor left. So that is why if you try to construct RAM cells, that is why if you try to construct RAM cells, which will be called as dynamic RAM if they are made out of one transistor and one capacitor, so you have to refresh the memory of this capacitor. For example, if I tell you to hold water into a glass for 15 years, even if it is kept in sunlight, but you have to give me one glass of water, the same glass of water after 15 years. So what will you do? You will keep that glass in sunshine, and whatever amount of water is lost because of sunshine, you will fill it daily. Will you or will you not? Yes or
Yes,
no?
sir.
So same happens to the electronic components also. If you manufacture a circuit using capacitor, the capacitor has to be refreshed at regular intervals, so that whatever value of charge, logic 1 or logic 0, it is holding, that should be maintained, right? So but you know, removing 5 transistors from the circuit, because in static RAM you had 6 transistors and no capacitors, while in your dynamic RAM you have 1 transistor and 1 capacitor, so 5 transistors are removed. So transistors are very costly components. So if you are able to do 1 by 5 times reduction in their construction, you are significantly able to reduce the cost of that device that you are manufacturing, which comes to be known as dynamic RAM. So that is why it is called as dynamic. This, it has a mechanism of dynamism. It changes very rapidly. That is why there should be a refresh of capacitor after regular intervals of time. So the way we have introduced static RAM, we have interfaced static RAM to the 8086 CPU. It is not the same way in which dynamic RAM will be introduced, right? So the slots for putting the static RAM will be separate, and the slots for putting the dynamic RAM will be separate. For dynamic RAM, a supporting structure of refreshing the capacitors should be required, right? So on that note, first of all, let us list out the advantages of dynamic RAM. Several kilobytes to megabytes and not byte or nibble based. I mean, whenever you are trying to construct a dynamic RAM, you won't talk about a few kilobytes or megabytes. I mean, you will be talking about larger memories of several orders of megabytes, right? You will be manufacturing maybe, say, a RAM of 2 GB, RAM of 4 GB. You will never listen to that you will manufacture a RAM of 1 kilobyte, right? RAM should be of the orders of several megabytes, right? And in those times, several kilobytes was also a valid term, but in these days, it should be of the order of several megabytes, and that has to be dynamic RAM, because ultimately, in that case, only this assembly of 1 transistor and 1 capacitor will be commercially viable. It will be commercially viable, because the refresh mechanism, it is same for 1 transistor and 1 capacitor, or for an assembly of 1 transistor and 1 capacitor, which are 10,000 in number. So the refresh mechanism remains the same. That is why it is cost effective to manufacture the dynamic RAM having a larger set of memory, right? And it has got a high packaging density. Now you can well imagine that earlier you were having 6 transistors which were able to do the task of 1 cell. However, here you have 1 transistor and 1 capacitor. So on the chip, they will be consuming very less space, and that is why they have got a higher packaging density. Then they are low cost, obviously, for the reasons that 5 transistors are lost. They also have low power consumption. This is obviously very true, because instead of having 6 devices, you are having only 2 devices to construct 1 cell, and that is why the power consumption will also be very less, despite of the fact that there is a refresh mechanism involved. However, the disadvantages of dynamic RAM are this capacitor discharging refresh cycle is there. So capacitor discharging refresh cycle has to be there, and that requires additional hardware. Then operating speed is little bit reduced, not reduced to an extent that we will be compromising with the performance of our program, but the operating speed is little bit reduced as compared to the cache memory. SRAMs are used in cache memory. DRAMs, they are not used in cache memory, but their fastness is also very, very good. It is not so poor that we cannot use it, right? Then additional hardware for refresh mechanism is required, right? So let me just show you how refresh mechanism functions, what all hardware you will require for that refresh mechanism. So this on the screen you see, let me just open it by another viewer. Yeah, so on the screen now you see a dynamic RAM interfacing module, right? So here this dynamic RAM, you can see that these individual chips, they are of 16K cross 1. 16K locations are there, and they are able to store only 1 bit each. That means 16K locations are there, and since 1 bit is used in each memory locations, so this chip that you see here is of 2 bytes only. Is this understood by everyone? This chip that you see here is of only 2 bytes. Is this thing understood by everyone? Yes or no?
No, sir.
See, 16K cross 1 means what? Every location will be of 1 bit. Earlier it was of 8 bits. Now here it is only of 1 bit. Every location, 16K locations are present there, and it is of 1 bit each. Sorry, it will not be of 2 bytes. 16K locations are there. That means 2 raised to the power of 4 and 2 raised to the power of 10. So 2 raised to the power of 14 total addresses are there, and they are able to store 1 bit location each. So that is not of 2 bytes, that is of several bytes. But you can see that there are various sets of 16K cross 1 RAM cells attached here, which are capable of storing only 1 bit of memory per address. And you can see that they have got these lines which are connected to some refresh mechanism. There is this refresh mechanism hardware which is connected to every cell, right? And if you want to connect it to the 8086 system, this is the address decoding logic that you are going to use from A14 to A15, whatever is your logic. You are going to connect the address mechanism from here, and there has to be this separate refresh mechanism which will have a counter and a refresh timer to timely refresh them to their original values, right? So that is why this additional mechanism is introduced. Rest of the mechanism, whatever we have studied for your static RAM, will be applicable here also. But in addition to that, this refresh cycle has also to be there for this dynamic RAM. So is this diagram understood by everyone?
Yes, sir.
So this is just a representation. I have not illustrated it for a particular case, but just to show you that a separate refresh timer is required, separate refresh counter is required, I mean a refresh mechanism together with the addressing logic, and this DRAM will come in a different format so that can be interfaced, right? So this is the problem with the dynamic RAM, but we usually use this as the actual RAM of the system. Right. And about input output mapping and interfacing, we have already talked in the laboratory session. So that's what we are doing here. I mean, in the laboratory section, we have already talked about input output mapping, and we have seen some experiments where we were able to interface a thermometer, and then we were able to interface a screen to that, which was a 7-segment display screen. So we were able to interface that to our system also, right? So this is it about this lecture. From the next set of lectures in the coming 2 weeks, I will try to bring some interesting programs, and we will discuss those programs so that our practicing on this 8086 becomes good, right? So any doubts in today's lecture? Anyone with any doubts in today's lectures can ask their doubts. Or if there are no
Sir,
doubts, yeah.
can you clear dynamic RAM once again?
Dynamic RAM, you just need to know it from the theoretical perspective that with dynamic RAM interfacing with the conventional address mechanism that we have read for static RAM, there is a separate circuitry for refresh mechanism that is required. Right, so this is what you need to know, and the interfacing of that is a separate issue. So system designers usually will be taught that thing, but from the perspective of a programmer, we should know that dynamic or static RAM can be attached, and attaching static RAM is easy by the mechanism that we have studied. And for dynamic RAM, you will need a separate refresh mechanism, and that is usually the work of system designers, right?
Yes, sir.
Right. So that's what we need to know about this dynamic RAM, static RAM interfacing. In fact, for ROM, we have various types: EPROM, EEPROM, and regular ROM. So there are various kinds of ROM. These days, you must be aware that the content in ROM can also be changed, right? So ROMs are also more or less writable these days, but they are not as easy to write as the RAM chips are. So these types of RAMs and ROMs, they are taught in digital logic course, where you will be taught how to make a DRAM or ISRAM. So that's a topic of that course, and that is taught to mostly the electronics and communication engineers in depth, because they will be designing the systems. So that's for them. But for our purposes, this much knowledge is sufficient. But if you want to, if you want me to elaborate on that, I can have a separate session on how to construct latches, flip flops, and how actually memory is there in a logic gate. Because for logic gate, by now I guess you only know that if you apply two inputs to a AND gate, which are both ones, you will be getting the output as one, or otherwise it will be zero. But by using these logic gates only, you will be able to store some element in them. So how that storing is done, I was expecting that you must have been knowing all this. But if you do not know that, I can have a separate session and tell you that, okay, in this way, a single bit is stored inside a circuit. So that's what we can do, if you want me to do that in some lab session. Right. So, any other doubts? Anyone else? Okay, so I will close this session for today.